All right, so we're starting with multi-degree of freedom vibrations here. We're going to consider first the matrix form of the equation of motion. We're now going to be considering an n degree of freedom, simple mass spring damper system, but n degrees of freedom rather than just a single degree of freedom previously. You can apply any of the techniques that we've covered in this class for finding equations of motion, and then you'll find that they are, first of all, you'll find n equations, not just one or two or three, you'll find n of them, whatever n is equal to. And they'll have the form, for the system shown here, they'll have the form mi times xi double dot plus ci times xi dot minus xi minus 1 dot plus ci plus 1 times xi dot minus xi plus 1 dot plus ki times xi minus xi minus 1 plus ki plus 1 xi minus xi minus 1. And all of that equal to the external force Fi of t. And then this is true for I equals 1, 2, all the way up to n. And here we'll have x0 of t being defined as 0. So just so you're aware, the motion of this ground, this is x0 of t. So it's 0 by definition. And then also x of n plus 1 of t, this is also defined to be 0, which is the motion of the ground on the far right. All right, so we have n equations where, as listed here, they have coupling in the damping terms, and they have coupling in the stiffness terms, as shown for this system here. This system does not have any coupling in the mass terms or the inertial terms, but you can easily get that through coupling things like rotating, like a pendulum coupled to a cart will give rise to that. Okay, so I said we have n of these equations, and it becomes much easier if we write this out in terms of matrix equations. And so that's what we're going to do. We're going to expand these equations into a mass matrix times an acceleration vector, a damping matrix times a velocity vector, and a stiffness matrix times a displacement vector, and then a forcing vector. And when I say vector here, I mean that in terms of like a one-dimensional matrix or an n by 1 matrix is what I mean. I don't mean like directional vector.
Should it be xi minus xi plus 1 in the last term?
Yeah. Yeah, it should be, yeah. Yep. All right, so let me scroll down here. We're going to start off with our mass matrix. And as shown here, this is going to be M1, 0, dot, 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 0, then another 0 in the next row, M2, dot, 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 0. We'll have going down vertically, dot, 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 0 for both the first two columns. And then in the last row and column, we'll have Mn. So this is a diagonal mass matrix. You may not always have a diagonal mass matrix, but there are ways to make it diagonal if that is important to you, through something like Cholesky decomposition, or like a square root decomposition as well also works. And this will be multiplied by a acceleration vector, x1 double dot, x2 double dot, dot 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 xn double dot. So we're going to call our mass matrix here. We'll say this is big M. And for right now, I'm going to use a double underline to indicate a matrix. And this is defined as the n by n mass matrix. And this here, we're going to end up calling x double dot vector. And this is the n by 1 acceleration vector. Okay, then we're going to have a damping matrix. We're going to have C1 plus C2. In the first entry, minus C2, and then C2 plus C3. Then we'll add our dot dot dots. In the last column, we're going to have 0, 0, dot dot dot. In this case, it will be Cn plus 1. 0 here. Oh, no dots there. 0 here, and then dot dot dot. Multiplied by the velocity vector, x1 dot, x2 dot, xn dot. We'll call this matrix here, we'll use a big C, the double underline, and we'll call this is the n by n damping matrix. And this vector we'll say is x dot, which is the n by 1 velocity vector. And then we're going to have a stiffness matrix, which will be very similar to our damping matrix. In this case, it will be K1 plus K2, minus K2, minus K2, K2 plus K3, dot 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 0, dot 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 0. Zeros down here, zeros here. And then Kn plus 1. Multiplied by the displacement vector, which is x1, x2, dot dot dot, xn. And then lastly, equal to a forcing vector, which will be f1 at t, f2 at t, dot dot dot, all the way up to fn at t. And then we'll call the stiffness matrix. We'll say this is big K, defined to be the n by n stiffness matrix. This vector multiplied by the stiffness matrix is, we'll just say here x, and this is our n by 1 displacement vector. And lastly, we'll say f of t, defined to be the n by 1 n by 1 forcing vector. We can call all of this should be equation 2. So as for the system we've defined here, we end up with a diagonal mass matrix and then a banded damping and stiffness matrix, meaning that the stiffness matrix really lives in this band. And a similar thing for the damping matrix. That does not mean that you couldn't have a spring that connects the first mass to the last mass, and in which case you would end up with a non-zero term you'd end up with a non-zero term here. And then there'd also be a non-zero term right above this one as well. And then you'd have another term added to this third entry here. So in this case, we don't have any springs that are coupling non-adjacent masses, but you can easily have that as well. And in some cases, you can end up with, you could consider these matrices to be sparse, meaning that there's lots of zeros in them. But in some situations, you end up with very dense matrices where there's not a single zero anywhere in it, and none of these are banded. You have non-zero entries everywhere. Okay, so the reason why we did all of this is really so that we can rewrite this big equation, or rewrite all of this and equations into a single equation, and we can write that as M matrix times X double dot vector plus C matrix X dot vector plus this K matrix times X is equal to F of T. So we can reduce down our n equations of motion into a matrix equation, which we can then write down into just a simple expression that looks very much like the expression for a harmonic oscillator that we saw in the previous chapter. Yeah.
Why is there a negative C2 in the matrix and negative K2?
That is a great question. So the question is, why do we have a minus 2 here, or minus K2 here, minus K2 here as well? And why do we have a minus C and a minus C2 there, right? If we come back to our original equation of motion, you'll see that for xi, we'll have a minus xi minus 1 there, as well as here. And also for the next entry here. So if we go look at our first oscillator, and we'll just deal with the C's here, we got x1 dot here and x2 dot here. This term will multiply by the x1 dot. Let that just be. This term is going to multiply by the x2 dot, and that's going to give us C2, ignoring the C1 for right now. We'll ignore that C1. X1 dot minus x2 dot. If you come look at our original equation of motion right here, and you say that, not that one, come look at this one right here, you say I is equal to 1, you end up with C2 times the quantity x1 dot minus x2 dot. That's where that negative sign comes in. And if I is equal to 2, in this equation you'll get C2 times x dot 2 minus x1 dot. And that's where the negative sign here comes in. And similar for the stiffness as well. Okay. So the fact that you end up with a minus K2 here and 1 here is not an accident. It's actually really a fundamental part of mechanics. And that's where we're going now. So first of all, you should note that the mass matrix, in fact, all of these matrices are symmetric, meaning that they're equal to their transpose. And this is a fundamental result of mechanics. It's generally called the Bett-Maxwell reciprocity theorem, but it also goes back to like Newton's third law, where there's an equal reaction for every action. Okay, so just to very briefly touch on Bett-Maxwell reciprocity theorem, we're going to consider, in this case, I've drawn a beam here, but this is true for any system, well, we'll talk about when it's not true in a moment. I've drawn a linear cantilever beam here, keyword here being linear. We're going to consider a situation where we apply a force Fa of t here, and then we measure the response at location B. We call that UB of t. And then we'll consider the opposite case where we force at B and then we measure at A. And in that situation, provided that if Fa of t is equal to Fb of t, then the displacements UA of t will be equal to UB of t. Meaning that if you want to measure the response or the motion of this system for a given force at one if you want to measure the response of the system at many locations, but you only have one sensor, but you can force it at any location, you leave your one sensor at a single location, and then you just go and, let's say you're using a hammer, you just take your hammer, you hit the structure at many different locations, each hit being a single measurement, and then you'll be able to measure the entire response to the system used through this reciprocity theorem as well. If Fa and Fb are not equal to each other, then the reciprocity theorem still holds, but then you end up with the integrals of the force times the displacement are equal to each other, or in this case, the work done is equal to each other. You're not going to be tested on this anyway. This is just to let you know. The key thing to note is that your mass matrix, your stiffness matrix, and your damping matrix should all be symmetric. And if they're not symmetric, then you made a mistake somewhere. It means that you made a mistake in deriving your equations of motion. That being said, we're looking at a linear system here. And a lot of the systems that you've been deriving equations of motion are inherently nonlinear just due to the kinematics of the problem. This is true for linear systems. Once you have nonlinearity, you can't build a matrix out of that. You can build a linear mass stiffness damping matrix, and then you end up with a nonlinear forcing vector. We'll pretend it's a force typically. So this reciprocity theorem is always true for linear systems, period, end of sentence. It's only true for some nonlinear systems. For nonlinear systems, you've got to have both nonlinearity, and you've got to have some type of asymmetry in like the geometry of the system. Non-reciprocity is where you break this theorem, and that's like an active area of research, so not a topic for this class. Okay, real focus is on this. Really, the key to this entire chapter is this matrix equation, and everything we're going to do is going to be based on this matrix equation here as well, primarily solving it in general. Okay, any questions? Yeah.
Yeah, so for nonlinear mechanics, does that mean the matrices are not necessarily symmetric?
Well, you can't really build matrices out of nonlinear functions is the issue. That's the problem, because this is, matrices are a fundamental part of linear algebra. And when you've got nonlinear stuff, you end up with nonlinear algebra. So you can't build a matrix. But if you were to imagine that we had some type of nonlinearity, what you would do is you would add another vector here, and this would be plus something like x1 cubed, 0, whatever. And that's how you would add in this. And you would end up, if you were to try and solve this like numerically or something, you would treat that as a pseudo force. You'd bring it over here and say this is a pseudo force. You won't be asked to do anything like that in this class, though. If you take a nonlinear dynamics class, then this would pop up there, for sure. All right, any other questions? All right, we are going to move on and tackle modal analysis, which is really the core focus on how do we solve this equation. Okay, so we're going to rewrite our equation of motion just so we have it here at the top of the page. We'll have m x double dot plus c x dot plus kx is equal to f of t. And just to go back to the nonlinear for a moment, if you were to have a nonlinear system and you were to, add in some extra force term there, you would not be able to use the technique that we're going to cover here. It does not work in nonlinear systems, period. Which is why you would have taken an entirely different class in order to solve those equations. So all of the vibrations we'll do in this class are linear by just the nature of this class. Because you need entirely different tools and different techniques, and it comes out to being an entirely different way of thinking about problems in order to solve nonlinear problems, or nonlinear vibration problems. If you're interested beyond what I've said so far, come meet with me and I'll be happy to tell you all about it. Okay, so we want to solve these equations and determine the displacements x at t. That means x1, x2, x3, etc., all the way up to xn. We want to know an analytical expression for each of those. And we're going to use a technique known as modal analysis. If n equals 2, you don't necessarily need modal analysis. There are other approaches. But if n is anything other than 2, you need modal analysis. So we're just going to cover modal analysis because then you're not stuck being confused about what to use. It works for 2 or more degrees of freedom. You could maybe apply this to 1 degree of freedom. I've never thought about that, but it's not really, it should end up being the same as what we've already done, effectively. There's no reason to apply it to single degree of freedom because we already have better ways to solve it. All right, so we're going to assume the system is what's known as proportionally damped, and we're going to come back to what that actually means later on when we talk about what classical damping is or what damping is in general. For right now, we're going to say this is proportionally damped, and we're going to say that the C matrix is equal to some constant alpha times the mass matrix plus some constant beta times the stiffness matrix. Hence, the damping matrix is proportional to the mass and stiffness matrix. This is a type of damping also known as Rayleigh damping. It's a very common approach for modeling damping. Not to say that it's correct, but it is a useful and common approach. And this will be very useful when we deal with the modal analysis because it will, one, allow us to deal with damping in the first place. We will eventually be able to solve systems that don't have this type of damping, but that will be like a month or two from now when we deal with state space formulations. Okay, so we're just going to list out what the steps for modal analysis are, and then we're going to go through each step in detail, and then when we do the example, we'll apply each step in detail as well, because there's a lot to it. All right, so the first, we're going to formulate and solve an eigenvalue problem for the undamped and unforced system. So we're going to ignore the forcing, we're going to ignore the damping, and we're going to focus on the undamped underlying system. This gives us what are called natural frequencies and mode shapes. So for single degree of freedom, we had one natural frequency, omega n. For n degree of freedom system, n degree of freedom linear systems, we will have n natural frequencies, or equal to the number of degrees of freedom. That's something that's not true in nonlinear systems. You could have more natural frequencies than degrees of freedom. Hence why this technique just breaks down. And mode shapes, we'll talk about what those are. I don't think I have any examples here, so I'll probably try and pull some examples of mode shapes of like what they actually look like for like an airplane or something out of my research. We're going to get natural frequencies and mode shapes. This will allow us to then define what we call the modes of vibration of the system. We're then going to do a technique called mass orthonormalization to mass orthonormalize the mode shapes. We'll then go and define modal coordinates, and we'll use those to decouple the equations of motion through a modal transformation So effectively what we're going to end up doing is we're going to use this modal analysis technique to transform this coupled set of n equations into a set of n uncoupled equations, in which case we'll now have n single degree of freedom oscillators that we can solve using what we did in chapter 2. That's the goal of this technique. Once you solve for the homogeneous and particular solutions of those decoupled modal coordinates, we can then go and do what's known as modal superposition, which will combine all of these together, basically just adding up the response of each mode together. We're going to go through this. We're going to start the steps for this, and then we're going to continue next week. All right, so like I said, this relies on superposition, meaning that we're adding up different solutions together. So as a result, it's only valid for linear systems. A fundamental feature of nonlinear systems is that superposition doesn't hold, meaning you cannot solve separately for a homogeneous and a particular solution and add them together. You can't do that in nonlinear systems. It does not work. You'll end up getting a solution that doesn't match what actually happens. Lots of interesting stuff arises in nonlinear systems is what I'm getting at. Okay. All right, we're going to start by formulating and solving the eigenvalue problem for the undamped, unforced system. Again, we're going to forget about the damping, we're going to forget about the forcing, and we're going to deal with them later. So that gives us the following equation of motion, which is the mass times the acceleration plus the stiffness times the displacement. And I've gone ahead and dropped the underbar notation here just to keep things cleaner and simpler. Okay, it says dropped function notation, but that's not what we've done. We've dropped the underbar. So next we're going to provide an ansatz, and we're going to use the same ansatz that we've used previously, except we're going to use it in a complex form. And we're going to involve a vector as well. We're going to say that the vector displacements, x of t, are equal to a scalar e to the j omega t, where j is the imaginary constant, times some vector big X of amplitudes. So this is the complex form of what we did in single degree of freedom, where rather than having a cosine of omega t, we now have e to the j omega t. So it's just a complex version. And instead of having a single amplitude, we now have an amplitude vector with n entries. J here is equal to the square root of -1. And then from there, we can find the acceleration vector, which will be equal to minus omega squared e j omega t times the amplitude vector. We're going to go ahead and substitute our ansatz into our equation of motion, and then collecting like terms, we will get that minus omega squared big M plus this big K, all of that multiplied by this amplitude vector times e to the omega t. All of that must be equal to a 0 vector. Okay, so e to the j omega t cannot be equal to 0 for all time, first of all. Secondly, it's a scalar, not a vector, so it certainly can't be equal to the vector 0 here. That leaves that either this whole quantity is equal to 0, or just the x by itself is equal to 0. The big X by itself being equal to 0 is just a trivial solution, so it's still a valid solution. It's just a very uninteresting solution. And as a result, that means that, oops, drew too much. Everything in this box, that must be equal to 0. And then this ends up being an eigenvalue problem. Or what this ends up implying is that the determinant of minus omega squared m plus k, that must be equal to 0. And this is where we're going to get our characteristic equation. which will be of the form some constant an times omega to the 2n plus dot 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 plus some constant a1 omega squared plus some constant a0 is equal to 0. Which we will recast as an times lambda to the n plus dot 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 plus a1 lambda plus a0 equal to 0. And so now we have an nth order polynomial where n is equal to the number of degrees of freedom. So if you have 10 degrees of freedom, you have a 10th order polynomial you have to solve. And when you use these things in practice for something like if you're using like a finite element model, you're generally thinking about thousands of degrees of freedom. And so you end up needing to solve, if you wanted to find every single natural frequency or every single omega, you would need to solve a thousandth order polynomial. And so when you get to that level of scale, there are other techniques for this kind of stuff. In this class, probably the highest you would go up to is like 3 degrees of freedom. It's probably the highest you go up to in terms of like a homework assignment. On like an exam, it would be 2 degree freedom. Because the calculations take time. They're not necessarily hard once you've done it several times, but they just take time. It just takes a lot of time. Okay, so the goal now is to solve for lambda. And you'll find that there's the same number of values of lambda as there are degrees of freedom, as we just talked about. And once we know lambda, then we can find the natural frequencies or the omegas. And by doing so, we will get that the ith natural frequency is equal to the square root of lambda I. And this is our ith natural frequency for I equal to 1, 2, up to n. And we only consider positive values of this square root because it doesn't make physical sense to have a negative frequency. I mean, mathematically it exists, but physically that doesn't make any sense. Okay, so the natural frequencies are going to be ordered from lowest to highest, always. So the first natural frequency will be the lowest value, and the nth natural frequency will be the highest value. As computed here, these will have units of radians per second. And you can convert that to hertz by dividing by 2 pi. So once we have our natural frequencies, the next thing we want to do is go and find what are known as the mode shapes, or we want to find the eigenvector for each eigenvalue. We'll call those xi. And to do this for each lambda, we're going to substitute that into our equation. Although, hold on a second, this should be just lambda here, not lambda squared. So for each lambda or for each omega, we're going to plug that into this equation. And just to be clear, this is minus omega I squared. So you can either plug in omega I squared or you can plug in lambda I in here. We'll then go ahead and solve for each xi. We'll end up finding that there aren't enough equations to to find a unique solution to this equation. And then we'll find that there's actually an infinite number of solutions to the equation, which implies that the mode shape can be scaled to arbitrary amplitude. And we'll come back to that and touch on that when we actually go and do this with numerical values. And you'll see what I mean by that. And then we'll just say here that this xi here, this is our ith mode shape. Again, I equals 1 to so on to n. And I'll try to bring some examples of mode shapes for you guys to see. All right, so then the normal modes of vibration are the set of natural frequencies omega I, the mode shape xi, true for I equals 1 to up to n. So we have n natural frequencies, n mode shapes, n modes of vibration, and the modes of vibration each have a natural frequency and a mode shape themselves. A mode of vibration is not just the natural frequency, it's not just the mode shape, it's the pair together. Okay, so the mode shapes have an arbitrary amplitude, this is something I just mentioned, and they satisfy the following orthogonality conditions. So the first one is that if you take xi transpose, multiply it by the mass matrix, and then multiply by xi here, this will be equal to, I'm going to use a script m here, or m sub I, and this is what we'll say is the modal mass. I'm going to add the underbars here because the modal mass is just a scalar. And I need to move this on over. We're going to add another condition here. If you compute this using different mode shapes, so x, let's not use j. So x sub r times the mass matrix times xs. This will be equal to 0 for r not equal to s. So what this means is that the mode shapes are mass orthogonal. They're orthogonal with respect to the mass matrix themselves. They're not orthogonal with respect to each other unless your mass matrix is proportional to an identity matrix. We will use this, and the condition I'm about to write, we will use this later when we go to do the modal transformation. And these conditions will allow us to decouple the equations of motion. Okay, we can do the same type of product, but for the stiffness matrix. So if we have xi transpose times xi, this will be equal to, we'll just say some script k sub I. We'll just say that's the modal stiffness. And likewise, if you compute this for different modes, you'll find that it equals 0. So they also have stiffness orthogonality. And the nice thing about this is that if you compute the fraction, the script ki divided by script mi, or the modal stiffness divided by the modal mass, this is equal to the natural frequency squared. Okay, in the second step, we're going to focus on mass orthonormalization of the mode shapes. I've mentioned before that the mode shapes have arbitrary amplitude, and it's convenient to choose an amplitude that makes the modal mass equal to 1 or equal to unity. And to that effect, we're going to say that we're going to use a scaled mode shape phi sub I equal to some constant alpha I times big Xi. And then our goal is to find this alpha I, whatever this constant alpha is. Our goal is to find that such that if we compute the product phi I transpose M times phi I, this will be equal to 1. So if we go and we'll write this out here, and then we'll expand it, phi transpose M phi I. This is equal to alpha I xi, that transpose M times alpha I xi. Alpha I is a scalar, so we can pull it out, and we'll get alpha I squared times xi transpose M xi. Excuse me. And we want that to be equal to 1. From there, we can solve for alpha I, which will be equal to plus or minus the square root of 1 divided by xi transpose M times xi. Or equal to 1 over the square root of the modal mass. All right, we're going to finish the next 3 lines, and then we're going to be done. So after computing alpha I, we'll then know what this phi I is, and it's just equal to alpha I times xi. From there, we're going to form what we call the mass orthonormalized modal matrix, or just the modal matrix. This is a capital phi here, and it's now a matrix. So this is capital phi matrix equal to the collection of these mass orthonormalized mode shapes, where each column represents or contains a single mode shape. And then these satisfy the conditions that the modal matrix transpose capital phi M times phi, this is equal to an identity matrix, and phi transpose K phi is equal to a diagonal matrix of the natural frequencies squared. And we're going to use these conditions to decouple the equations of motion, and we'll do that on Monday.